Hi there, and welcome to this film which is all about stoichiometry, but this time involving solutions. And it's the last of the films that I'm going to make about the quantitative chemistry topic of the IB Diploma chemistry course. Although it's about solutions, it's very much supposed to bring together a lot of the things that we've done in this topic. And as there's meant to be a progression through these films, I'd really strongly suggest that if you're getting here having not yet practiced and fully understood what's gone before, that you probably stop and go back a little bit. But hopefully by the end of this film you're going to be able to combine your knowledge of moles in solutions as well as mole ratios in balanced equations, and you're going to carry out some stoichiometry calculations that involve solutions. And by doing this, hopefully we're going to consolidate our understanding of some of those calculations that we've been looking at throughout this topic. Okay, here's our first example. What volume? You might be thinking, oh, gas laws, PV equals nRT, but this is a solution, right? Because we're given a concentration here, 1.06 moles per dm cubed hydrochloric acid. What volume of it, I'm asked, is needed to neutralize 25 centimeters cubed of 0.98 mole per dm cubed sodium hydroxide? Well, here's our sodium hydroxide. Here's our hydrochloric acid. What do I know about both of them? Well, there's 25.0 centimeters cubed of that. Its concentration is 0.98 moles per dm cubed. And I know about the acid that its concentration is 1.06 moles per dm cubed. What I don't yet know is the volume of it that I'm going to need to react with that sodium hydroxide. So first of all, let's just write a formula for volume here. Remember, we're not dealing with gases, so we're going to dealing with solutions. We know that C equals N on V, and we know that V equals N on C. What are N and C here? Well, we've got to be a little bit careful. We're here talking about what volume of acid, so we need to use the number of moles of acid and the concentration of the acid. It'd be easy to confuse these numbers because some of them are not talking about the acid, but they are concentrations and volumes. I don't know the number of the moles of the acid, although I am told its concentration. I know that the number of moles of acid is related to the number of moles of sodium hydroxide. In fact, I can write an expression saying that the number of moles of HCl is related to the number of moles of sodium hydroxide. I can check if my relationship is true the way I've written it. There's one of them and one of them, so the number of moles of HCl is indeed equal to the number of moles of sodium hydroxide. So as soon as I've found the number of moles of sodium hydroxide, the number of moles of NaOH, which equals the concentration of NaOH multiplied by the volume of NaOH, then I can find the number of moles of HCl. What's this equal to? Well, it's the concentration, 0.98 moles per dm cubed, multiplied by the volume in dm cubed, so 0.025, remembering that there are 1,000 centimeters cubed in a dm cubed. And what does that equal? That equals 0.0245 moles, as it happens, but 0.025 to two significant figures, because that is my least precise bit of data. So that's the number of moles of sodium hydroxide. I've already decided that's the same as the number of moles of HCl. So the volume of HCl is equal to the number of moles of it multiplied, divided by its concentration. Which of those do I know? Well, I know all of them now. So this is 0.025 divided by concentration, which is 1.06 moles per dm cubed, and that equals 0.023 dm cubed to two significant figures. I could equally well give my answer in centimeters cubed, nothing wrong with that, and that would be 23 centimeters cubed. But I'd have to make sure that I'm still using the same number of significant figures. Okay, so I suppose that's at the simpler end of the scale with stoichiometry that involves solutions. Let's move on to a slightly more complex thing. We're now combining solutions with gases, right? We're being asked what volume of hydrogen at STP. Hydrogen is a gas at STP. So I'm going to use the gas laws here. Will form when an excess of magnesium, So my magnesium's not going to run out. There's plenty of it to react with all the nitric acid. And what am I told about the nitric acid? I'm told that I've got 100 centimeters cubed of it, and its concentration is 0.100 moles per dm cubed. Okay, I'm asked to find the volume of hydrogen. Remember, this is a STP, so we could use V equals nRT over P, but we don't have to bother because it also equals the number of moles times the molar volume at STP, which equals the number of moles times 22.4. However, I don't know the number of moles of hydrogen. I only know that it's related to other things. Magnesium is in excess, so I'm not going to relate the number of moles of hydrogen to the number of moles of magnesium. I'm going to relate it to the thing that's going to run out. Number of moles of hydrogen is therefore related to the number of moles of nitric acid. Is this statement true the way I've written it? No, the number of moles of hydrogen is 1, the number of moles of nitric acid here is 2. So the number of moles of hydrogen is half the number of moles of nitric acid. Can I find the number of moles of nitric acid? Because if I can, then, HNO3. If I can find the number, that doesn't really look like HNO3, but unless I delete everything, it's going to have to stay like that. So the number of moles of HNO3 is equal to the concentration of it times its volume, which equals 0.100 moles per dm cubed multiplied by 0.100 dm cubed, because I've got 100 centimeters cubed, and that equals 0.0100 moles. Why have I given 3 significant figures? Because I've got 3 significant figures in my data. Okay, so I now know the number of moles of nitric acid. The number of moles of hydrogen is half that number, so the number of moles of hydrogen is therefore 0.00500 moles. And now the volume of hydrogen is 0.00500 moles times 22.4. Volume 0.000 times 22.4 dm cubed, and that equals 0.112 dm cubed, and you could give that in centimeters cubed, which equals 112 centimeters cubed. Okay. Last problem is going to combine all these things, but also with limiting reagents. Okay, so in the last one we had a limiting reagent, but we didn't have to calculate the number of moles of both. Here, I'm told about the lead nitrate, I'm told its concentration and its volume, I'm told about the volume of the hydrochloric acid that it's mixed with and its concentration. So I've got information about both these two substances. I'm asked about the mass of lead chloride here. Okay, so before I can find the mass, which remember the mass is equal to the number of moles times big M, which equals the number of moles times, where are we? 278.09. Okay, before I can find the mass of it, I need to know the number of moles of it. I know that the number of moles of it is related to the number of moles of HCl and the number of moles of lead nitrate, but I don't know which one to use yet because I've got information about both of them, so I need to figure out which one the limiting reagent is first. The number of moles of lead nitrate. What am I told about the lead nitrate? Well, I know its concentration and its volume, so the number of moles is C times V, which equals 1, the concentration 1.00, times the volume, which is 100 centimeters cubed, or 0.100 dm cubed, which is equal to 0.100 moles. So I've got 0.100 moles of lead nitrate. How many moles of hydrochloric acid do I have? Well, the number of moles of HCl is again equal to the concentration times the volume, which in this case equals 0.5 for my concentration, 0.5 moles per dm cubed, multiplied by 0.1 again, because this is in dm cubed, and that equals 0.05 moles. I can only give this number to one significant figure because I only had one significant figure in my data. So I've got 0.05 moles of that. Now, which one is going to be the limiting reagent? Well, if I had 1 mole of lead nitrate, I'd need twice as much hydrochloric acid. I don't have twice as much hydrochloric acid. In fact, I've got a lot less than twice as much, so the hydrochloric acid is my limiting reagent. Again, if I wanted to, I could do the actual ratio, which would be 0.1 divided by 0.05, and that's 2. This is putting the lead nitrate on top. In the balanced equation, the lead nitrate is 1 and the hydrochloric acid is 2, so that's a half, and 2 is definitely greater than a half, so in other words, there's more than enough of this thing here, and that's in excess. So I'm going to base my mole calculation here on the limiting reagent, right? Now I know that the number of moles of lead chloride is related to the number of moles of HCl. Is that statement true? No, it's not, because I've got 1 there and 2 there. So the number of moles of lead chloride is a half the number of moles of HCl, which equals 0.025. In actual fact, I can only give that to one significant figure, which equals 0.03 moles. And then I'm going to multiply that. I haven't written down the molar mass of lead chloride, have I? No, I don't think I have. Oh yes, I have. Is it there? 278.09. So that the mass of lead chloride equals 0.03 times 278.09. That number's got 5 significant figures. It's a data book value, but I can't use all 5 because I've only got 1 here. And that to one significant figure is 7 grams. Right. Well done if you've made it this far and you've watched all the films about the quantitative chemistry topic and you've understood everything and you've practiced everything. If there's anything from this film or any of the other films that you want to ask questions about it, do it soon so that you can practice these things and they can become almost like second nature to you. And if you want to post a comment on any of the YouTube films, that would be great as well.